The unsinkable pier, the artificial harbors that made D-Day possible. At 0330 hours on June 8, 1944, a Phoenix caisson designated A1-07 broke its tow line in mid-channel. The tugboat warden fought for 6 hours to regain control as wind and current pushed the 6,000-ton concrete block toward the French coast. The caisson measured 200 feet long, 60 feet wide, 60 feet high. It displaced more tonnage than a destroyer. It was hollow. It contained no propulsion system. It was drifting. This was the logistical challenge facing Operation Neptune in microcosm. 400 separate components of 2 artificial harbors crossing 100 miles of open water in convoys that stretched for miles. Concrete caissons, steel roadways, floating pontoons, breakwater sections. Each piece built in secret across Britain. Each piece essential. Each piece vulnerable to weather, to navigation error, to mechanical failure, to enemy action. The warden recovered the tow. Caisson A1-07 reached its assigned position off Omaha Beach. Workers scuttled it on schedule by opening 11 valves in precise sequence. It settled to the seabed and became one element in a breakwater that would shelter the largest invasion fleet in history until the storm came. The idea originated in failure. On August 19, 1942, Allied forces raided Dieppe, 6,000 troops, mostly Canadian, assaulted German positions in and around the port. The planners assumed they could seize the harbor facilities intact and use them to support the landing force. They assumed wrong. German defenders held every key position. The Canadians never reached the inner harbor. Of the 29 tanks landed, none returned. Of the 5,000 Canadians engaged, 3,600 became casualties. The raid lasted 9 hours. The lesson was absolute. Any future invasion of France could not depend on capturing an existing port. The Germans would destroy the facilities before abandoning them. Even if captured intact, ports would be within range of German artillery and air attack. The invasion would need its own harbors, harbors that could be built elsewhere and transported to the landing beaches, harbors that could operate in open water without natural protection. Prime Minister Winston Churchill had considered such a concept before. In 1917, during the First World War, he had proposed building artificial harbors using caissons and barges to support operations against German-held Belgian ports. Events overtook the plan. The war ended before construction began. But Churchill remembered. On May 30, 1942, 10 weeks before the Dieppe raid proved the necessity, Churchill wrote a memorandum to Admiral Louis Mountbatten, Chief of Combined Operations. The memorandum read, "They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves." The difficulties were considerable. To support an invasion force of the planned size would require harbor capacity equivalent to Dover, Britain's second-largest port. Dover had been built over centuries. Its breakwaters were stone and concrete set on bedrock. Its piers were massive permanent structures. Its facilities had been designed for commercial shipping in peacetime conditions. The artificial harbors would need to match that capacity while being built in months, transported across the channel, assembled under potential enemy attack, and operated in all weather for at least 3 months. The specifications bordered on fantasy. 2 complete harbors, each capable of handling 7,000 tons of supplies per day. Each harbor to include breakwaters extending approximately 2 miles to create sheltered anchorage, floating piers to allow ships to unload regardless of tide state, roadways from the piers to the beaches, flexible enough to handle a 30-foot tidal range, all components to be prefabricated in Britain and towed to Normandy, assembly to be completed within 14 days of D-Day. Lieutenant General Frederick Morgan, Chief of Staff, to the Supreme Allied Commander, examined the requirements and determined that success would require technical innovations across multiple engineering disciplines. Breakwaters that could be positioned in water too deep for traditional construction, piers that could rise and fall with the tide while supporting loaded trucks, roadways that could flex with wave action without breaking, anchoring systems capable of holding structures weighing thousands of tons in tidal currents and storm conditions. The design work began in October 1942 under conditions of absolute secrecy. Multiple design teams worked in parallel on different components. Brigadier Bruce White coordinated the overall effort for the War Office. The Admiralty controlled all maritime aspects, including towing and positioning. The Ministry of Supply managed construction contracts. Inter-service rivalry complicated every decision. The Admiralty wanted one solution. The Army engineers wanted another. The civilian contractors, caught in the middle, tried to build whatever they were told to build, while materials, labor, and time all ran short. 3 types of breakwater were developed. Each addressed different water depths and wave conditions. Each required different engineering approaches. The gooseberry breakwaters used obsolete merchant ships and naval vessels deliberately sunk to form barriers in shallow water. 70 old ships were selected. Their cargo spaces were sealed. Their superstructures were cut down. Their bottom plates were fitted with scuttling valves, codenamed corncob. These block ships would be positioned first, providing immediate shelter for landing craft and small vessels in the days immediately following the invasion. The Phoenix caissons formed the primary inner breakwater. These were massive hollow concrete structures, cellular in design, subdivided internally to provide structural strength and controlled flooding. 6 different sizes were designed, designated A through C with numerical suffixes. The largest, Type A1, measured 204 feet long, 55 feet wide, 60 feet high. Weight, 6,044 tons. The smallest, Type C1, measured 176 feet long. All were designed to be towed across the channel while floating, then sunk in position by opening internal valves to flood the cells. Construction required 330,000 cubic yards of concrete, 31,000 tons of steel reinforcement, 1.5 million yards of steel shuttering for the forms. Production involved 19 major construction firms across Britain operating at more than 30 coastal locations. 15,000 workers poured concrete day and night. 213 caissons were completed between June 1943 and August 1944. The construction sites used existing dry docks, tidal basins, and specially prepared beaches. At Southampton, the King George V dry dock could accommodate 8 caissons simultaneously. At Lepe on the Solent, 6 Type B, 2 caissons were built and launched sideways into the water using winches and ramps. At Conway in North Wales, construction took place on tidal flats. At Cairnryan in Scotland, military engineers built and launched caissons under Army supervision. The concrete had to cure underwater. Fresh water was unavailable in sufficient quantities, so seawater was used. The salt accelerated some aspects of curing, but introduced long-term durability concerns that didn't matter because the caissons only needed to last 90 days. Quality control focused on watertight integrity and structural strength during towing. Each caisson underwent hydrostatic testing before acceptance. Some failed. Caisson A 1-01 developed structural cracks during construction and was scrapped. Others developed leaks during towing and had to be abandoned. Several sank at their moorings in British waters before D-Day. The attrition was expected and planned for. Extra caissons were built to replace losses. The bombardon. Floating breakwaters formed the outer line of protection in deep water where caissons could not be sunk. These were cruciform steel structures, hollow, with internal buoyancy chambers. Each bombardon section measured 200 feet long with a beam of 25 feet. Draft, 19 feet. Total height, 25 feet. The cruciform cross-section was deliberate. The horizontal arms remained below the water surface, weighted with ballast. The vertical components provided buoyancy and structural rigidity. The shape was designed to absorb wave energy through mass and drag. 93 bombardons were fabricated using 20,000 tons of steel. Each section was built in shipyards across Britain, launched, towed to assembly points, and connected to adjacent sections using chain and shackles. Spacing between sections, 48 feet. Total length when deployed, approximately 1 mile of floating barrier. The concept came from Robert Lochner, who initially proposed inflatable fabric bags as floating breakwaters. Model testing at the National Physical Laboratory in Teddington showed promise but revealed vulnerability to damage. The design evolved to rigid steel construction. Over 300 scale model tests established the hydrodynamic characteristics. The cruciform shape reflected wave energy most effectively while minimizing steel weight per foot of barrier. Inside the breakwaters, the pierheads provided the actual unloading positions where ships could tie up. Codename Spuds. These were floating steel pontoons mounted on 4 telescoping legs. Each leg measured approximately 80 feet long. The legs could be extended hydraulically to rest on the seabed. The pontoon then jacked itself up above the water level or allowed itself to float with the tide while sliding on the fixed legs. This permitted the pierhead to maintain constant elevation above water, regardless of tidal state. 23 pierheads were ordered. Each measured 80 feet by 60 feet. Capacity: sufficient to berth coasters and medium-sized cargo ships displacing up to 4,000 tons. Cranes and other cargo handling equipment were mounted on the pontoon decks. The legs could be adjusted to maintain level even if the seabed was irregular, or if one leg penetrated soft mud more than the others. The whale roadways connected the pierheads to the beach. These were articulated steel bridge spans resting on floating pontoons codenamed Beetles. Each whale span measured 80 feet long and weighed 30 tons. The spans were constructed from steel plate bolted to cross girders. 1 in 6 spans included telescoping joints at the center to accommodate length changes caused by tidal flow and wave action. The design permitted the roadway to twist vertically up to 40 degrees between ends, while still supporting loaded vehicles traveling at 25 miles per hour. The Beetles were pontoons, either steel or concrete, that supported the whale spans. Steel Beetles were fabricated from plate. Concrete Beetles were precast in sections, 1.5 inches thick, then assembled and reinforced with cast-in-place concrete ribs. Each beetle measured approximately 40 feet long by 12 feet wide. Buoyancy was calculated to support the whale span plus the weight of trucks crossing the roadway. In shallow water near shore, Beetles were fitted with simple spud legs that could be lowered to rest on the beach, converting the floating roadway to a fixed causeway. 670 Beetle pontoons were built, 120 whale spans. Total roadway length per harbor, approximately 2 miles. The sections could be towed as complete assemblies. 6 spans connected with their supporting Beetles, forming a 500-foot-long roadway unit that flexed with wave action during the tow. The anchoring system presented particular challenges. Traditional ship anchors were inadequate for the forces involved. A 6,000-ton caisson in tidal current generated loads that would drag conventional anchors through any seabed short of bedrock. Alan Beckett designed a specialized anchor with exceptionally high holding power. The kite anchor, as it became known, featured multiple flukes angled to penetrate and grip the seabed. Holding power per ton of anchor weight exceeded anything previously available. The Admiralty was skeptical. Tests proved Beckett correct. Kite anchors were used to secure the whale roadways and spud pierheads. The Admiralty still refused to use them for the bombardons, preferring conventional mooring systems. This decision would prove costly. By May 1944, the components were ready. Phoenix caissons floated at assembly points along the south coast at Selsey Bill, Dungeness, and Portland. Bombardon sections waited in Southampton Water and the Solent. Whale and Beetle units were staged at multiple locations. The old ships designated for gooseberry duty were moved to Portland and Poole. Tugs were assembled from across the British Merchant Fleet and the Royal Navy. 85 tugs would tow 500 separate towing operations to move all components to Normandy. The invasion began at 6:30 hours on June 6, 1944. By evening, Allied forces held beachheads on 5 beaches. The harbor components began crossing the channel on June 7th. The first Gooseberry block ships were scuttled on June 7th at low tide. By June 9th, all Gooseberry lines were complete, providing immediate shelter for landing craft. Phoenix caissons began arriving on June 8th. Positioning required precision. Each caisson had an assigned, numbered location on the planned breakwater line. Tugs maneuvered the caissons into position using differential towing to achieve the final alignment. When correctly positioned, the scuttling crew opened 11 valves in careful sequence. Water flooded the internal cells. The caisson settled slowly, taking approximately 90 minutes to reach the bottom. If the flooding was unbalanced, the caisson would list, possibly capsize. The valve timing had to be perfect. By June 14th, half the Phoenix caissons were in place. Mulberry A, off Omaha Beach, was ahead of schedule. Mulberry B at Arromanches was on time. Pierheads were being positioned. Whale roadways were being assembled. The first supply ships were beginning to tie up at the spud piers. Cargo was flowing. The engineering had worked. The harbors were operational. Then the weather changed. At 0600 hours on June 19th, the wind began rising from the northeast. By 1200 hours, it was blowing force 6, defined as wind speed 25 to 31 miles per hour, classified as strong breeze. Gusts reached 40 miles per hour. By evening, the wind increased to force 7, near gale. Sustained winds 32 to 38 miles per hour. Gusts exceeded 60 miles per hour. The wind direction was worst possible for the Normandy coast. Northeast winds had a long fetch across the North Sea. Through the Dover Strait, along the English Channel, the waves built progressively over hundreds of miles of open water. By the evening of June 19th, significant wave height off Normandy exceeded 5 feet. By June 20th at 1800 hours, wave height exceeded 8 feet. The storm continued through June 20th and 21st. The wind did not drop below force 6 until June 22nd. This was the worst June storm recorded in the Channel in 80 years. The timing was catastrophic. The Gooseberry blockships held, being sunk on the seabed, they could not be moved by wave action. They provided the intended protection for landing craft and small vessels in shallow water. The Phoenix caissons suffered. Wave action against the massive concrete walls generated enormous pressures. Some caissons had been sunk in positions where the seabed was softer than expected. Scouring occurred as wave action eroded bottom sediment from around the base. Several caissons settled unevenly, tilted, and eventually broke apart. Wave overtopping introduced water into caissons that were supposed to remain partially hollow for stability. The internal water sloshed with wave motion, generating dynamic loads that exceeded design limits. Caisson walls cracked. Some collapsed entirely. 21 of the 30 Phoenix caissons at Mulberry A were destroyed or damaged beyond repair. At Mulberry B, losses were less severe. The orientation of the beach and the presence of offshore sandbanks diverted some wave energy, but damage still occurred. Approximately one-third of the Phoenix caissons at Arromanches suffered significant damage. The bombardons failed completely. Every single bombardon broke loose from its moorings. The conventional anchors and chain systems that the Admiralty had insisted upon could not hold against the storm loads. Free-floating bombardon sections, each weighing hundreds of tons, became battering rams. They smashed into Phoenix caissons, doing more damage than the waves themselves. They crushed landing craft. They broke pier structures. They became hazards to navigation that persisted for days after the storm abated. The spud pierheads and whale roadways suffered catastrophic damage at Mulberry Harbours. Pier structures broke apart. Whale spans separated from their beetle pontoons. Steel twisted. Connections failed. By June 22nd, when the wind finally dropped, Mulberry A was a wreckage field. Concrete and steel debris littered the beach and the approaches. Some pier structures remained partially intact, but were damaged to beyond immediate repair. Mulberry B at Arromanches survived with heavy damage but remained operational. The British engineers had paid closer attention to mooring procedures. The kite anchors held. Some piers were damaged but could be repaired. The Phoenix breakwater, though reduced, still provided partial shelter. The immediate decision was pragmatic. Mulberry A was abandoned as a complete harbor. Salvageable components were towed to Arromanches to repair and extend Mulberry B. American forces at Omaha Beach reverted to direct beach landing of supplies. Landing ship tank vessels grounded on the beach at high tide, opened their bow doors, discharged cargo and vehicles, then refloated on the next high tide. The method was crude but effective. The Americans discovered that the soil conditions at Omaha permitted heavy equipment to operate on the beach without bogging down. This was luck. It could not have been predicted before the landing. Mulberry B, reinforced with components salvaged from Mulberry A, continued operations. Cargo throughput averaged 7,000 to 9,000 tons per day, sometimes exceeding 10,000 tons, from June 7th through November 19th, 1944. When operations finally ceased, after the capture of Antwerp, provided a deep water port. Mulberry B handled 2.5 million men, 500,000 vehicles, 4 million tons of supplies. The harbor had been designed to operate for 90 days. It functioned for more than 5 months. The cost of construction was enormous. 20 million pounds sterling at 1944 values. 45,000 workers employed at peak. 144,000 tons of concrete. 105,000 tons of steel. The production effort diverted resources from other critical programs, including merchant ship construction and destroyer building. Dry docks used for bombardon fabrication could not build Phoenix caissons. Steel allocated to bombardons could not be used for landing craft or reinforcing concrete beetles. In retrospect, the bombardons were the most costly mistake. 20,000 tons of steel consumed to build structures that failed in their first major storm and caused more damage than they prevented. The Admiralty's insistence on using bombardons despite protests from civilian engineers proved wrong. The Admiralty's refusal to use kite anchors for the bombardons proved disastrous, but the core concept was validated. Artificial harbors could be built, transported, assembled, and operated successfully. The Phoenix caissons worked. The gooseberry block ships worked. The whale roadways and spud pierheads worked when properly moored. The engineering was sound. The execution under combat conditions was remarkable. Individual stories emerged from the chaos. Tugs that fought for hours to hold position in the storm. Work crews that repaired damage while under air attack. Engineers who improvised solutions when components failed or went missing. Royal Navy divers who went down to inspect caisson damage and report on structural integrity. Salvage teams that recovered usable equipment from the wreckage at Omaha Beach and transported it to Arromanches. Commander John Hughes Hallett, one of the senior naval officers responsible for the harbor operations, later wrote that the Mulberry Project demonstrated what could be achieved when military necessity, engineering ingenuity, and industrial capacity aligned toward a common goal. He noted that no single element was particularly revolutionary. Caissons had been used before. Floating piers existed. Articulated roadways were not new. But the scale and the complexity of integrating all elements into a functional system under combat conditions was unprecedented. The technical achievements extended beyond the harbors themselves. The hydrographic surveys required to identify suitable seabed conditions were conducted under enemy observation by small craft operating at night. The meteorological forecasting required to plan the towing operations pushed the state-of-the-art. The logistics of coordinating 500 separate tows across 100 miles of open water while maintaining invasion secrecy tested command and control systems to their limits. The harbor components that remain today serve as monuments. Phoenix caissons still stand off Arromanches, forming an artificial reef popular with divers. 2 caissons rest in Portland Harbor, preserved as Grade II listed structures. Others were used after the war for various purposes. In 1953, several Phoenix caissons were towed to the Netherlands and used to close dike breaches during flood relief operations. Some whale roadway sections were used to replace bombed bridges in France, Belgium, and the Netherlands. 3 whale spans ended up at Fort Dagenham, where they served as ramps for cars being loaded onto ships. The lessons learned from the Mulberry Harbours influenced post-war port engineering. The jack-up pier concept, where platforms could be raised above storm surge levels, found applications in offshore oil exploration and military forward operating bases. The use of large prefabricated caissons for breakwater construction became standard practice. The understanding of wave dynamics and floating structure behavior advanced significantly. But the primary lesson was strategic. The invasion of Normandy succeeded without capturing an intact port. The artificial harbors provided the logistical support during the critical initial phase when the beachhead was vulnerable and supply lines were stretched. Without the Mulberries, the invasion force would have been dependent on beach landing of supplies in whatever weather conditions prevailed. The storm of June 19th would have disrupted operations regardless, but with Mulberry B still functioning after the storm, the supply chain continued with reduced capacity rather than collapsing entirely. General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, stated after the war that the Mulberry Harbours were essential to the success of Operation Overlord. He noted that skeptics had derided the concept as fantasy when first proposed. The engineering challenges seemed insurmountable. The resource requirements seemed prohibitive. The operational risks seemed unacceptable, but necessity drove innovation. The failure at Dieppe proved that capturing a port would be impossible. Therefore, the invasion force would bring its own ports. The alternative was postponement or cancellation of the invasion. By mid-1944, postponement was not viable. Soviet forces in the east were demanding the opening of a second front. The longer the delay, the more time Germany had to strengthen Atlantic wall defenses. The weather window for a channel crossing in favorable conditions was limited. The tides and moon phases required for the landing occurred only on specific dates. Missing the June window would force delay until July or August, with declining prospects for success. The Mulberry Harbours made the invasion possible on the timeline required. They were not perfect. They were not optimal. They were adequate. In military operations, adequate at the right time is often sufficient. The storm that destroyed Mulberry A and damaged Mulberry B demonstrated the limits of the engineering. The structures were designed for normal summer conditions in the channel. The design wave height was based on historical meteorological data suggesting that June storms of the severity experienced were rare. The 93-year return interval for a storm of that magnitude meant the probability of encountering such conditions during a 3-month operational period was low. But low probability is not zero probability. The storm occurred. The consequences were severe. Yet the operation continued. Mulberry B was repaired and remained functional. American forces adapted their supply methods to work without a complete harbor. The logistical chain continued to feed the expanding beachhead. By July, Allied forces had broken out of Normandy and were advancing toward Paris. The engineering failure at Mulberry A paradoxically validated the broader strategic concept. Even with one harbor destroyed, the invasion succeeded. The loss caused difficulties, but not defeat. The redundancy of having two harbors provided resilience. When one failed, the other continued. When harbor capacity proved insufficient, alternative methods filled the gap. Leon DeLong, an American engineer present at Omaha Beach during the storm, watched the Phoenix caissons being torn apart by wave action and the battering of loose bombardons. He observed that fixed structures in exposed locations were inherently vulnerable to extreme weather. From that observation came the concept of jack-up offshore platforms that could be elevated above storm surge levels when severe weather threatened. His post-war work on jack-up oil rigs and other offshore structures traced directly to lessons learned during the June 19th storm. The human cost of the Mulberry operations was modest compared to the combat casualties occurring simultaneously ashore. Several workers were killed during construction accidents in Britain. Some sailors died when tugs sank during the channel crossing. A few Royal Engineers were lost during the assembly and positioning operations under enemy fire. But the total casualties numbered in dozens rather than thousands. The project killed more through industrial accidents than enemy action. The secrecy surrounding the Mulberry Harbours during construction was extraordinarily successful. German intelligence gathered fragments of information about unusual construction activity at British ports, but failed to identify the purpose. Reconnaissance aircraft photographed the assembly sites, but interpreters could not determine what was being built. The code names revealed nothing. A phoenix was just a word. A whale could mean anything. Bombardon had no obvious connection to breakwaters. Gooseberry sounded like an agricultural project. The first German awareness of the artificial harbors came after D-Day when reconnaissance flights over Normandy photographed the components being towed across the channel and assembled off the beaches. Even then, initial intelligence assessments considered them to be temporary expedients rather than complete harbor installations. Albert Speer, German Minister of Armaments, later described the Mulberry concept as an example of Allied engineering superiority and termed it simple genius that Germany had not considered. The complexity of the project generated extensive documentation. The War Office issued more than 130,000 prints of working drawings for the Phoenix caissons alone. Design specifications filled volumes. Construction contracts detailed requirements for materials, dimensions, tolerances, testing procedures. Towing plans specified routes, speeds, convoy formations, weather limits. Assembly instructions diagrammed positioning, anchoring, connecting procedures for each component type. This documentation has allowed detailed post-war analysis. Engineers have examined why certain components succeeded while others failed. Hydrodynamic studies have modeled wave forces against the Phoenix caissons and identified design weaknesses. Structural analysis has revealed why some caissons broke apart while others remained intact under similar loading conditions. The June 19th storm has been hindcast using modern meteorological models to determine actual wave heights and wind speeds for comparison against design specifications. The analysis confirms that the bombardons were fundamentally inadequate for the conditions encountered. The design assumptions about their mooring systems were wrong. The conventional anchors failed at loads well below storm levels. The chain connecting adjacent bombardon sections transmitted loads that the chain links could not withstand. The free-floating sections caused cascade failures as they collided with other harbor components. The Phoenix caissons performed closer to design expectations, but still suffered unexpected failure modes. Wave overtopping was more severe than predicted. The internal water sloshing created dynamic loads that the structural design had not fully accounted for. Seabed scour was more extensive than geological surveys had suggested possible. The combination of factors produced failures that individually might have been survived but collectively exceeded structural capacity. The whale roadways and spud pierheads worked well when their moorings held. The articulated design absorbed wave motion effectively. The telescoping joints accommodated tidal range. The buoyancy calculations proved accurate. But when mooring systems failed, the structures failed catastrophically. Without secure anchoring, wave action simply swept the piers and roadways away. The success of Mulberry B compared to the failure of Mulberry A came down to small differences in execution. The British engineers used kite anchors and paid more attention to mooring procedures. The positioning of Phoenix caissons at Arromanches was more favorable regarding seabed geology. The offshore banks northeast of Gold Beach diverted some wave energy. The cumulative effect of these differences was survival versus destruction. Military operations depend on such margins. Small differences in terrain, weather, timing, execution often determine outcomes. The Mulberry Harbours demonstrated that engineered systems under combat conditions operate at the edge of their design limits. When margins are thin, small variations produce large consequences. The artificial harbors also demonstrated the importance of redundancy in military logistics. Having two harbors provided resilience. The American ability to supply forces over open beaches provided an alternative when Mulberry A was lost. The capture of Cherbourg on June 26, though the port facilities were extensively demolished, provided another supply route. No single point of failure could collapse the entire logistical system. The remains of Mulberry B at Arromanches are now protected as historical monuments. The French government has preserved the Phoenix caissons that still stand offshore. The Beach Museum displays components and tells the story. Visitors can wade into the water at low tide and touch the concrete that formed the breakwater. The scale becomes apparent. These are not small structures. Each caisson is the size of a building. The memorial aspect matters. The Mulberry Harbours represented the culmination of British engineering under wartime pressure. 45,000 workers built the components while bombs were falling on British cities. Materials were diverted from other critical programs. Engineers worked without precedent, inventing solutions to problems that had never been solved before. The time frame was compressed beyond anything peacetime engineering would attempt. And it worked. The failures are also worth remembering. The bombardons failed because the Admiralty overruled the civilian engineers who warned they were inadequate. The mooring systems failed because proven technology was rejected in favor of conventional methods that didn't work. These failures cost lives and resources. They degraded harbor capacity at a critical moment, but they didn't prevent success. The operation continued. The invasion succeeded. This is the nature of military engineering in wartime. Systems are designed to specifications based on best available information. Systems are built using available materials and labor. Systems are deployed under operational constraints that don't allow for perfect conditions. Some systems work, some fail. The overall mission succeeds or fails based on whether the working systems are sufficient, despite the failures. The Mulberry Harbours were sufficient. Not perfect, not optimal, not invulnerable to the worst storm in 80 years, but sufficient to support the invasion during the critical months when no alternative existed. By November 1944, when Mulberry B finally ceased operations, the Allied armies had advanced hundreds of miles into France. The port of Antwerp was operational. The logistical situation had fundamentally changed. The artificial harbors had served their purpose. Some historians argue the Mulberry Harbours were unnecessary. They point to the success of American beach landing operations after Mulberry A was destroyed. They note that most supplies ultimately came through Cherbourg and other captured ports. They calculate the cost in resources and conclude the artificial harbors were an expensive diversion from more important programs. This analysis ignores the strategic context. Planning for the invasion began in 1942. At that time, there was no certainty that ports could be captured quickly or intact. The Dieppe raid demonstrated that attacking a defended port frontally would be disastrous. The strategic bombing campaign aimed at destroying port facilities meant that even captured ports might be unusable for months. The invasion could not wait for ports to be repaired. Therefore, the invasion force needed its own ports from the beginning. The fact that alternatives ultimately worked does not mean the Mulberry Harbours were unnecessary. They provided the initial capacity that allowed the buildup of forces during the vulnerable early phase. They demonstrated Allied capability to overcome the port problem, which affected German defensive planning. They were insurance against the possibility that Cherbourg could not be captured or that its facilities were too badly damaged to restore quickly. The artificial harbors were a calculated risk that paid off. The cost was high. The engineering was challenging. The execution under combat conditions was difficult, but they worked long enough and well enough to serve their purpose. That is the standard by which they should be judged. The technical legacy of the Mulberry Harbours extended far beyond World War II. The floating pier designs influenced offshore oil platform development. The large-scale prefabrication and towing of major structures became standard practice in civil engineering. The use of hollow concrete caissons for breakwaters spread globally. The understanding of wave dynamics and structural loading in marine environments advanced significantly. The organizational legacy mattered as well. The Mulberry Project demonstrated that massive engineering undertakings could be completed on compressed timelines when properly organized. The coordination between military, government, and private industry became a model for subsequent large projects. The parallel development of multiple solutions to the same problem, then selecting the best approach based on testing, became standard engineering practice. The men who built the Mulberry Harbours knew they were participating in something unprecedented. The workers pouring concrete in British ports understood their work would support the invasion, but didn't know when or where. The security was absolute. Families were told nothing. The press published nothing. German intelligence learned nothing useful. Only after D-Day did the full scope of the project become public knowledge. By then, the components were already crossing the channel. The first Phoenix caissons were being sunk. The Gooseberry block ships were settling into position. The engineering concept was becoming operational reality. And the men who had designed and built the artificial harbors waited to learn whether their calculations were correct and their construction was adequate. For 12 days, the answer was yes. The harbors worked. Ships unloaded. Supplies flowed. The beachhead expanded. Then, the storm came and tested every component to destruction. Half of one harbor was destroyed. The other survived with damage, but the mission continued. The artificial harbors had provided just enough capacity for just long enough to make the difference. That was all they needed to do.